This section provides a brief, intuitive definition of probability and conditional probability. This brief presentation was organized by Dr. Alemi and narrated by Yara Alemi. Probability is a quantitative measure of uncertainty. When we are sure that an event will occur, we say it has a probability of 1. When we are sure that an event will not occur, we assign it a probability of 0. When we are completely in the dark, we give it a probability of 0.5, or note that it has a 50% chance of occurrence. Values between 0 and 1 measure how uncertain we are about the occurrence of an event. If there are a total of n mutually exclusive possible events, and m of these are event A, then the probability of event A can be calculated as the count of times the event occurred divided by the count of times any event could have occurred. Visually, this can be shown in a Venn diagram. The rectangular blue area shows the universe of possibilities. The circle shows all the ways in which event A occurs. The probability of event A is defined as the yellow circular area divided by the blue rectangular area. We have provided now a simple definition of probability as the ratio of counts of the observed event to the counts of all possible events. But the question remains, is this definition practical? The universe of possibilities is an important part of defining the concept of probability. Of course, counting the universe of possibilities is an impossible task. However, inside electronic health records, this is significantly easier. Inside the computer, the universe is well defined and contained. We know exactly how many patients we have data on, and we know exactly how many of them have had a particular disease. We can easily count probability of diseases and events inside the electronic health record. SQL can help us count the number of mutually exclusive events so we can have a good estimate for the universe of possibilities. Therefore, we have a practical way to count the number of possible events, and our earlier definition is both valid and practical. Plus, this definition allows us to calculate many difficult concepts, such as the union of two events, joint occurrence of two events, and conditional probability. The probability of two overlapping events can also be calculated as a fraction of the universe of possibilities. Here we see a Venn diagram with events A and B. The red area shows the situation where both events have occurred, and the remainder of the yellow circles show where one has happened but not the other. The probability of either one of the two events occurring is the two overlapping circles divided by the universe of possibility, or the rectangular area. However, you have to be careful not to double count the red area. The probability that both events occur together is given by the red area divided by the universe of possibilities. Conditional probability is calculated by shrinking the universe of possibilities. Of all the possibilities, the only thing that is now possible is the event that has occurred, or in other words, the condition in the conditional probability. In SQL, this translates to filtering the data using a where command. The where command reduces the massive data in the electronic health record to a smaller subset where event A has occurred. When we know that event A has occurred, then the universe of possibilities in the Venn diagram is shrunk to the blue circular area. We see here that the area where A and B co-occur is still red, and the rest of the area where A occurs but B does not is blue. Therefore, the probability of B given A is now calculated as the red area, where both A and B occur, divided by the reduced universe of possibility, which is the circular area of A. The point is that conditional probability is calculated using a reduced universe of possibilities. Data in a sample or data in electronic health records can always be reported as a contingency table. A contingency table is a count of how two or more events co-occur. The count of joint observations are provided in the inner cells of the table. The total number of times that both events occur together is given on the left upper cell as A. The number of times neither event is present is given as D. In the margins, the row and column totals are provided. For example, the total number of times that event A is present is A plus B. The total number of times that event B is present is A plus C. In the contingency table, the universe of possibilities is given by A plus B plus C plus D. That is our entire sample of data, and therefore represents the count of all the events that are possible. Usually, in an electronic health record, we analyze the data by patients, so the universe of possibilities is all unique patients. The emphasis in this analysis is to make sure we count only distinct patients. We should not double count a patient if they have had many encounters. One way to do this is to use the count distinct SQL command. Remember, if the unit of analysis is the patient, then the universe of possibilities is the number of unique patients in our data. Using our definition of probability, the probability of event A is calculated as the number of times it occurs, A plus B, divided by the universe of possibilities, A plus B plus C plus D. Similarly, the probability of the occurrence of event B can be calculated as the number of times that event B occurs divided by the universe of possibilities. The probability of event B not occurring is the number of times it does not occur, or B plus D, divided by the universe of possibilities. You can see from these calculations how our definition of probability helps us calculate the probability of events, even tricky events like negative events or events not occurring. Conditional probability is calculated by shrinking the universe of possibilities to the occasion where the condition has occurred. For example, to estimate the probability of event A occurring once we know that event B has already occurred, the universe is shrunk from A plus B plus C plus D to just A plus C, which is all the situations where the condition, i.e. event B, has occurred. Now, the conditional probability of event A occurring given event B is calculated by the frequency of event A in the reduced universe, i.e. A divided by the reduced universe, also known as A plus C. The takeaway here is that conditional probabilities should be calculated in the reduced universe where the condition has already occurred. Our definition and the concept of shrinking the universe can help us calculate conditional probabilities correctly. Many students make mistakes in calculating conditional probabilities from contingency tables. The easiest way to avoid making an error is to remember to always first calculate the reduced universe and then the conditional probability. Here, the conditional probability for event B given A is shown. Note how the universe of possibilities is now reduced to only situations where the condition, aka event A, has occurred. Pay close attention to the condition and you will not make mistakes in these types of calculations. If you follow this procedure, then you will also not have any difficulty in calculating conditional probabilities that involve double negatives, such as what is the probability of event B not occurring, given that event A has also not occurred? It is
often difficult to understand what is meant by these negative events, but following our procedure, we will make quick work of this problem. First, reduce the universe to the condition. In this case, we reduce it to a situation where A has not occurred, which here is C plus D. Then, examine the frequency of event B not occurring, which is D. Now you can easily set up the probability of event B not occurring, given that event A has not occurred. Let's try our hands at some sample data. Here we have 19 total patients, so that becomes our universe of possibilities. 10 of these patients have above normal blood pressure, and 9 have blood pressure in normal ranges. In the inner cells, we have the number with normal and abnormal blood pressure that were diagnosed with hypertension. Now, what is the probability of having a hypertensive patient? To calculate this, we use the number of hypertensives divided by the universe of possibilities, which is our total number of patients. This time, let's explore what the probability of having a hypertensive patient is, given that your patient has a blood pressure above normal. Again, the probability is calculated from the number of hypertensives divided by the universe of possibilities. However, this time, our universe of possibilities is now reduced to the group of patients with above normal blood pressure. Before we leave this topic, let's quickly discuss the relationship between probability of an event and odds of an event. Odds of an event is the ratio of the probability of the event occurring over the probability of the event not occurring. One can calculate the odds from the probability and vice versa. The probability of an event is just the odds plus 1 divided by the odds. Both probability and odds are used to express uncertainty about the occurrence of an event. Some people prefer to talk about odds of an event, and others prefer to talk in terms of probability. However, there is one advantage to talking in odds. Probability always ranges from 0 to 1, while odds can be 0 to a number larger than 0. In other words, odds have no upper bound. Of similar note, after probability of 0.8, the increase in odds is matched with smaller increases in probability. For example, odds of 9 to 1 is the equivalent of a probability of 0.9, but odds of 19 to 1 is equivalent of the probability of 0.95, and odds of 99 to 1 is equivalent of the probability of 0.99. So that was a 0.05 jump and a 0.04 jump in probability, but a huge jump in odds. As odds increases to very large numbers, they add a very small amount to the probability of an event. Also note that the odds of an event can never produce a probability of 1. This has been the lecture on conditional probability and how it can be thought of as probability in the reduced universe of possibilities. Thank you for listening.